Assalamu alaikum, it's me Ismine Yasmin, student of Electrical Engineering from Namal Institute, Miyawali. My project integration of bit manipulation extension to a SweRV core of RISC-V processor and its verification using standard tool is being supervised by Dr. Tasadduq Hussain. This is the strategic flow involved in the success of our project. Processor is the brain of computer responsible for executing instruction and performing calculation. There are the numerous processors available in the market and continuously growing with technology advancement. Due to dynamic nature, exact count is not possible as they are regularly introduced to meet specific performance and power usage requirements. Processors are classified on the basis of their architecture. RISC-V is not just an architecture, but it is an open source that provides security features. The world where data breaches is the constant concern. Having secure processor is crucial. There are more than 10 billions of the cores available in the market and thousands of engineers are working on it globally. Seeing all the cores of RISC-V, we selected SweRV to make it useful for the embedded IoT and other applications. This is the performance graph basically showing performance comparison of SweRV EH1 Core with other processors core, in which x-axis are showing the name of processor and y-axis are showing the performance in core mark per megahertz. SweRV is the 32-bit in-order 9-stage pipeline processor with dual issue and superscalar operated at 1 GHz frequency. For the 28 nanometer technology, it can work up to 1.8 GHz. There are 4 stall points in it and it has 2.3 dMIPS per megahertz and core mark of 4.9 core mark per megahertz. Following are the features that are possessed by the SweRV EH1 core. It is based on the RISC-V architecture with superscalar properties and in-order execution pipeline. It is based on the Harvard architecture and it is basically designed for low power application. The major challenge faced by the SweRV is absence of bit manipulation extension. Bit manipulation involves the manipulation of individual bits introduced by ARM and Intel for increasing performance, reducing power loss, increasing efficiency, and reducing code length. We are integrating the instructions of ZBA, ZBB, ZBS, and ZBC for various operations. For the applications of embedded system, IoT, cryptography, and data compression, it's mostly used. Nowadays, it's being used in IPv4 subnetting, graphic programming, and locking secrets. The following are the basic tools, techniques, and technology that we are using in our project. In our project, we are basically trying the microarchitecture of the SweRV EH1 core and integrating bit manipulation extension in it and performing a functional verification for this. We are working on the FPGA porting and testing the modified core on real-life applications. Now we will be discussing the design and development strategy. This is the basic hardware hierarchy of our project, in which we are taking the top.sv files and simulating it using HDL simulator. This is the folder repository which contains different files and we are making changes in the color blocks. This is the basic hardware architecture of SweRV EH1 core, showing all the stages independently. By accessing all the code files and tracing signal by signal, inputs, outputs and other signals, we have drawn the microarchitecture of SweRV EH1 core by ourselves. For making the view clear, we have expanded the pipeline stages here. These are the instructions that we are integrating in the SweRV EH1 core. We are integrating the instructions from ZBA, ZBB, ZBC and ZBS. These are the stages of the core in which we made modification based on the type of instruction of bit manipulation. Let's see the demo of our integration process. This is the modified microarchitecture of the SweRV EH1 core. This flowchart shows the general purpose for handling bit manipulation instructions. It starts with the instruction fetch and decode. Then check if instruction is a bit manipulation instruction. If it is, it determines the type of bit manipulation, ALU or multiplier, and perform the corresponding operation. If it is not a bit manipulation instruction, it follows the base ISA flow. Finally, the result is computed and stored. This is the flow of any file through the variator. We are using variator to convert a file into the object file that is used for functional verification. We created various test benches, run them through variator to check the functionality of every instruction, and this all improve the overall performance. We are creating more test benches to bring more efficiency. By using these commands, we run the code initially and obtain the original cycles of the core. These are the results obtained after the integration of bit manipulation extension, in which the cycle has been reduced, showing the performance improvement. We are using various tools and boards for the FPGA porting of modified core. In future, we will be testing the modified core results through real-life applications. Thank you for your time.